Okay, let's dive right into this explainer and explore one of the most fascinating mysteries of the universe. And it starts right in our own backyard. Whether you're a dedicated student of astronomy or, honestly, just someone who looks up at the night sky and wonders, this is for you. We're going to unpack the actual science of cosmic darkness today, breaking down exactly why our universe looks the way it does. It's a really brilliant exercise in physics, the behavior of light, and cosmic perspective. So get ready to take some mental notes as we illuminate the void. Picture this. You're standing outside on a bright, sunny day, looking up at this beautiful, vibrant blue sky. It's something we literally see every day, so we completely take it for granted. But then, imagine climbing into a rocket ship and blasting off. The second you break through the atmosphere, that familiar blue sky just vanishes. It is instantly replaced by an endless, pitch-black darkness. It's an incredibly dramatic shift from vibrant blue to absolute black. And that observation brings us right to the core question driving our learning journey today. If the sun is so incredibly bright, why on earth is space black? Think about it. The sun is still shining just as fiercely out there in the void as it is down here. It's lighting up our entire solar system. So shouldn't all that brilliant, unfiltered sunlight make space incredibly bright too? It's a perfectly logical question, and honestly, it's one that pretty much every science student asks at some point. To answer this, we really need to wrap our heads around the sheer power of our local star. The sun is this enormous, unimaginably powerful engine. Every single second, it's throwing out a staggering amount of energy. Now, it takes just 8 minutes for that light to cross the vast distance of space and reach us here, warming the planet and giving us daytime. So space is literally flooded with this light, constantly. But if sunlight is everywhere, why isn't the space around us glowing? Well, here is the absolute most crucial point to understand. Light doesn't become visible to us just because it exists in a space. No, for us to actually perceive it, light must do one of two things. It must either travel directly into your eye from a source, or it has to bounce off something else first and then enter your eye. This 3-step journey, leaving the sun, entering the atmosphere, and bouncing into our eyes, is a fundamental rule of optics you'll definitely want to remember. Now, what's really cool is seeing how this rule plays out right here at home. On Earth, our atmosphere is completely packed with gas, mostly nitrogen and oxygen. So when sunlight enters this layer, it collides with billions and billions of these tiny gas molecules. This massive collision triggers a process called Rayleigh scattering. Because blue light travels as shorter, smaller waves, it gets scattered much more effectively by these tiny molecules than red light does. It literally paints our entire sky blue. Without this atmospheric scattering, our daytime sky would be as black as midnight. Section 1. The vacuum of empty space. So Earth's atmosphere is thick with molecules, which scatters light absolutely everywhere. But outer space is mostly a vacuum. It contains almost nothing at all. There are no tiny nitrogen or oxygen particles floating around out there. And because there's practically nothing for the sunlight to bounce off of or scatter from, the light just travels silently and invisibly in perfectly straight lines. If it doesn't hit anything, we simply can't see it. Wait a second though, if light isn't entering your eyes directly, you can't see it, which naturally begs the question, how can astronauts still clearly see the sun against a dark background? If the space around them is totally black, why isn't the sun hidden too? It's a great little test of the concepts we literally just covered. To really visualize this, imagine shining a flashlight through a perfectly clean, completely dust-free room. You can look directly at the flashlight bulb and see it's super bright, right? And you can clearly see the spot on the wall where the beam hits, but the beam of light cutting across the room itself, it remains completely invisible. Why? Because there's no dust floating in the air to scatter that light back into your eyes. Space is exactly like that hyper-clean room. Astronauts see the sun because that specific light is traveling directly from the star into their retinas. But the empty void around it, it stays perfectly black. Section 2. Seeing the sun and stars. All right, let's scale this up. This brings us to a historical puzzle known as Olber's paradox, which, fun fact, baffled astronomers for centuries. Scientists estimate there are hundreds of billions of galaxies out there, right? And each of those galaxies is packed with billions of stars. So, as a student of the cosmos, you have to wonder, why isn't the entire night sky glowing with blinding white light? If we look in any direction, shouldn't our line of sight eventually hit a star? Why on earth is the background of the universe black? Well, the answer comes down to time and distance. The universe is about 13.8 billion years old. Now, light travels incredibly fast, but it still has a speed limit, and it takes time to cross these unfathomable cosmic distances. The simple, mind-blowing truth is that many distant stars and galaxies are so incredibly far away from us that their light just hasn't even had the time to reach Earth yet. The universe simply isn't old enough for all of that light to have made the trip. And there's another really fascinating layer to this. Not only is the light taking its sweet time to get here, but the universe itself is constantly expanding. As those incredibly distant galaxies move farther away from us, the light they emit actually gets stretched out over space. It stretches into longer wavelengths, completely shifting out of the visible spectrum. So much of this stretched light becomes entirely invisible to human eyes. Between the vast distances and the expanding universe, massive areas of the cosmos remain utterly dark to us. Section 3. What astronauts actually see. So, when astronauts look out the window of a space station, they experience a view defined by just extreme, wild contrasts. When they look toward the sun, they get this dazzling, unsoftened sunlight because there's no atmosphere to filter it. But when they turn away, they witness an endless black background dotted with brilliant pinpoint stars. And against this deep black canvas, objects that reflect light, like our brilliantly shining moon or the Earth glowing brightly in blue, stand out with just unbelievable clarity. It makes space a stark, yet profoundly beautiful place. So, what is the big takeaway from our learning session today? I'd say it's this profound realization. The next time you step outside on a sunny day, look up. Truly realize that the gorgeous blue sky above you is not the natural color of space. It's literally just a thin atmospheric illusion, a trick of Rayleigh scattering played by billions of tiny gas molecules. Just beyond that incredibly thin layer lies a vast, mysterious ocean of absolute darkness. We really hope this explainer has illuminated the void for you today and helped you master some of these foundational concepts of physics and astronomy. Remember, every great discovery begins with curiosity. And hey, if the universe keeps expanding and light keeps stretching into invisibility, will future students one day look up at a sky that is completely, entirely empty? Keep asking those big questions, keep studying, and most importantly, keep looking up.